Thanks for attending today's webinar on unconformity uranium deposits. We're going to take a look at those from the spectral perspective. Now, this webinar is going to be mainly geared towards actual application users, but it looks like we do have a few people here who may not be as well versed in unconformity uranium deposits specifically. So this will have a little bit of information on the geology of the deposits as well, so that everyone can understand. The outline for today's webinar, we'll start out with a very quick intro to Spectral Evolution's line of field portable spectrometers, and then we will shift over to exactly why uranium is a topic of interest right now, a quick overview of example deposits, and finally, we'll see those deposits from the spectral perspective and how to utilize a field spectrometer to do so. Here is the OR-X series of field portable spectrometers that Spectral Evolution offers: the standard resolution or Express, high resolution or Explorer, and ultra high resolution or Expert. These models differ in spectral resolution, with the OR Expert giving you about double the resolution than you'd get with the OR Express, meaning you'll get more detail in your mineral spectra and key features that won't be present with the OR Express. If you're new to the technology or need a rundown on how this technology applies to the mining industry, I urge you to visit our YouTube channel, where you will find a previous webinar called Instant Mineral Identification, where I basically give an intro class to the technology. But today we are solely focused on how it's used in uranium exploration. These instruments go in a backpack and are taken into the field, and they're ran off lithium-ion batteries. Or you can use the instrument kind of in a core shack setting or maybe a lab style setting with a power supply. Two style contact probes are offered. So we've got a 10 millimeter spot size and a 3 millimeter spot size. These probes are rugged and durable and can take a measurement with one click of a button. It takes about 3 seconds to take a measurement. And if you're in the field, we offer a tablet that has a GPS that will display your data instantly. So this data is going to be in ASCII format. So if you're someone who's using third-party software like IOGAS or TSG, for example, you can just directly upload that. Why am I focused on uranium applications today? Well, that's because nuclear has been pushed as part of the green solution. So a lot of money has been put towards green energy lately. We really can't reach our lofty goals without nuclear. And by 2050, global nuclear capacity needs to double in order to reach net zero emission targets and in order to reduce the reliance on fossil fuels. So part of that zero emission energy plan includes nuclear because, according to the United Nations and World Nuclear Association, it is the cleanest, most reliable source of clean green energy. So in order to get to the temperature target that we're wanting, nuclear is the best solution to achieve that net zero carbon target. That's because nuclear is ranked as one of the most environmentally friendly generation sources, second to only one specific variant of hydropower, which measured against other power sources. In terms of uranium deposits, I mean, Canada is just absolutely killing it. Obviously, the major producing basins, for example, like the Athabasca, this in particular has about 60 years of mining, and it's really the premier high-grade uranium district. So we know a lot, especially spectrally, about this basin. And, they've been heavily studied, and we have lots of data from those areas. I do know, recently, within the past couple of years, there's a big basin deposit in Niger. So it's really starting to pick up throughout the world. Some of you here also may have been worked on Athabasca-style basins there in Australia. So, yeah, uranium is really picking up. For those of you who may not know anything about unconformity-associated uranium deposits, this is specifically for you, just a quick little rundown. So these guys consist of pods, veins, and semi-massive replacements of uraninite, which are overlaid by zoned quartz dissolution, kaolinite, pseudoite, illite, dryvite, and quartz alteration halos that are located near unconformities between Paleo to Mesoproterozoic siliclastic basins and metamorphic basins. So there's your geology 101 for that. Now, where the Athabasca Basin comes in is because early work on alteration mineralogy in this specific basin is basically the modern framework of exploration of white mica and clay mineralogy for other Athabascan style basins around the world. So this model here shown on the right, so this is a modified model of two end member sandstone models for egress type deposits in the eastern Athabasca Basin. So we've got quartz dissolution on the left and silicification here on the right. Intense clay alteration zones surrounding the deposits, such as the Cigar Lake here on the left, constitute natural geological barriers to the uranium migration in groundwater. And these are important technical geofactors in mining and ore processing. Now, the illite, kaolinite, chlorite alteration halos are going to be at the base of the sandstone, and they're several hundreds of meters vertical extent above the deposits. So this alteration typically envelops the main ore controlling structures. So if you see this area right here, so this is going to form like a plume shaped or more like a flattened, elongate, bell-shaped halo. So those typically start to taper gradually upward from the base of the sandstone. So you're going to be looking for, potassium, magnesium, aluminum ratios that will be diagnostic of the different clay types. And so we can actually see those different clay types spectrally. Hydrothermal ore relation alteration effects are also going to be superimposed. So the ore-related white mica alteration is going to be superimposed on the red hematitic paleo weathering alteration. So a lot of times, you'll see these hematite caps, which we'll see a little bit later. And, those very dark, coarse-grained hematite alterations, for example, you can see those above in the Cigar Lake here on the left. Hematite is going to be interpreted to be a very early diagenetic mineral. So here's an example of kind of what that looks like in the field. This figure here is from a hydrothermal alteration paper on uranium deposits that was posted in the Remote Sensing Journal by some researchers at the China University of Geosciences. So here you can see in the top left figure A, where you can see up here the red hematite caps, but also where the illite is located. So it's going to be lower. And we'll go more into great detail spectrally on that illite here soon. So this in figure C, this is a representative drill core. So, we can track the alterations of these uranium deposits with a field spectrometer, which we'll see here soon. Okay, so why use a field spectrometer for this application? Well, the hydrothermal alteration in these deposits are closely related to the uranium mineralization of the deposit. So you'd use a field spectrometer to take drill core measurements, for example, that will reveal the altered mineral assemblages, which have obvious zonation characteristics, like the type of white mica, the type of clay, and identifying that hematite, for example, as a uranium processing indicator. So we talked about those hematite caps as well. So you then take your spectral data and you'd use it for a multitude of things, whether that be true identification, maybe you're using it in tandem with other data sets, such as validating your hyperspectral survey data, maybe your geophysical surveys, etc. So again, this data that you take will work very well with other data sets in the sense that it almost completes a puzzle And it's just another tool in our geologist toolbox, if that makes sense. Okay, so now we're going to kind of move over and look at some spectral data that we typically see throughout these deposits. So this first plot that we're looking at, this is going to show the common alteration minerals that are typically found in the Athabasca Basin deposit. So this is going to include dravite, which is here in the red. You're going to see illite, which we'll go over in more detail here soon, kaolinite, and dickite. So we kind of talked about those different clays and being able to distinguish them as you're, say, measuring down your core. This is going to be a key thing to look for. So spectrally, we can actually distinguish between kaolinite and dickite, or whether you're looking at high temperature kaolinite or low temperature kaolinite, different things like that. The next plot we're going to look at are your chlorides. So this plot here is going to show the magnesium chloride here in the red. And the green, this is going to show a unique pseudoite, which is plotted. Next plot we're going to take a look at. So these are just going to be other minerals that are going to be observed as you're looking through core in these types of unconformity deposits. Obviously quartz, especially if you've got quartz dissolution, things like that. So in the red. Hematite is going to be big. So when we look at hematite, we're going to look in this lower region here. So we're looking at 700 to 900 nanometers. This is indicative of hematite. You also might encounter some rare earth. So blue here, I've got some monazite. Some of you might even encounter some carbonate. So this is a dolomite measurement. You might encounter that. And then finally, siderite. So I'm going to go back to my illite measurement because we're going to go a little bit more in detail on that. So I'm actually just going to send this to our EasyID software. Okay. All right, so before I get into it, this is our EasyID mineral identification software. Very similar to TSG if you've ever used that. The red line that you see is going to be a library spectrum. The blue line is going to be your target spectrum. This green box right here, since I am going to be focused in on illite in the 2200 nanometer region, I have added in a specific region there. So we're just going to focus on that. Now, in terms of tracking illite throughout these deposits, there's going to be two things that we're going to focus on. The position of that ALOH feature and the illite spectral maturity scalar, which are shown over here on the right. So you've got your ALOH, where it tells you your wavelength, and then the ISM, which is the illite spectral maturity, which will give you a value. Now, illite is typically one of the most common minerals identified in these types of deposits using hyperspectral technology. And there are different types that we're going to look for. Long story short, changes in the absorption peak wavelengths in these white micas here at the 2200 nanometer region are closely related to temperature and pressure. So this is strongly depends on the spectral resolution and the maximum and minimum values of that spectral absorption peak wavelength of the white mica, being illite and muscovite minerals. So at this 2200 nanometer region specifically. So a lot of times, when we're measuring drill core from different depths of these deposits, we typically see a trend in the 2200 nanometer position. So that means short wavelength illite, which is going to be characteristic of 2195 to 2202 nanometers, meaning, for example, my ALOH of this specific is at 2192. So this would be considered a lower wavelength illite. You also see more of a medium wavelength illite, that means that your position would kind of shift to the right. And that would be positioned around 2203 to 2212 nanometers. And then finally, you've also got a type that's going to be a longer wavelength illite. So meaning that your ALOH feature is going to be shifted even longer wavelengths to more of a 2213 to 2200 nanometer wavelength. So the absorption peak wavelength of these white micas, the illites, muscovites at 2200 is going to be governed by the aluminum content, and the changes in that aluminum content are caused by the replacement of different elements. So as the aluminum content increases, the absorption band here at 2200 nanometers is going to gradually shift to shorter wavelengths. The replacement process depends on temperature, pressure, and pH properties of that fluid. Now, previous studies, so again, this has been thoroughly studied, especially in the Athabasca Basin. These have proposed that the aluminum poor white mica may be related to low temperatures, whereas aluminum rich white mica may be related to relatively high temperatures. So kind of looking at where your white mica is positioned here using this scalar, ALOH scalar, this is only part of the puzzle. The other part is going to be looking at the illite spectral maturity. So this ISM right here. Now, illite spectral maturity is an important spectral parameter, especially if you're someone focused on the sericite group. So it's usually controlled by temperature and is useful for exploration. Now, this scalar is defined. You can actually see the equation here. So it's defined as you're basically taking the absorption peak of the illite at 2200 nanometers and dividing that by the absorption peak depth of the illite at 1900 nanometers. So a lot of times when you're measuring drill core, you'll notice differences in absorption peaks of the illite at 2200 nanometers, and the illite spectral maturity will be obvious. So you might have a situation where you've got a drill core from 3 different sections of your deposit. Maybe in an upper section where, say, your absorption peak of your illite at 2200 nanometers may be high, so greater than 2208 nanometers. And the illite spectral maturity is smaller than 0.8. So in this specific case, my value here is 1.39. That's pretty high. So a middle section of a deposit, you could, for example, find that absorption peak of the illite at 2200 nanometers gradually shifting to lower wavelengths, so less than 2203 nanometers, similar to this illite we have here. So my value here is 92.8. So this is shifted to shorter wavelengths. And, similar to this illite, you'll kind of notice that the illite spectral maturity is going to start shifting to greater values. So in this case, our spectral maturity is pretty high, again, 1.39. So what exactly does the spectral shift of the illite and the illite spectral maturity value tell us? So as a reminder, changes in the wavelength at 2200 nanometers are closely related to temperature and pressure. And the illite spectral maturity value is also controlled by temperature, making these 2 specific parameters useful for exploration. So that illite spectral maturity value of the white mica can often indicate the center of hydrothermal fluid activity. So the higher values here that you get, so we have a pretty high value, this would indicate that the temperature and pressure of the deep illite was greater than that of the shallow illite. So, you'll find that your values are going to kind of gradually increase from, say, an upper section to lower section of that deposit. So this specific measurement of illite, this would indicate to me that this was in a position in the deposit beneath the boundary due to the high value. So if this was from, say, that upper section of a deposit, my ISM would be a lot lower, say around 0.8. My ISM value here, this is indicating that this was from an, upper section. And this would tell you that the temperature of the short wavelength illite is higher than that of the upper section, meaning that the hydrothermal fluid here activity was probably located in that lower section close to maybe a fault and fracture zone. So again, you can use these two scalars to show that, the temperature of the fluid kind of gradually changes from relatively high temperatures at depth to relatively low temperatures in upper section of deposits. So this is really why we use the field spectrometer, because it can be beneficial to exploration as you can kind of track those hydrothermal fluids and continuous fluid alteration based on these spectral features. So if we had, hundreds and hundreds of drill core from different sections of the deposit, we could literally track that hydrothermal fluid based on the position of my ALOH feature and also the ISM. So this is going to give you, again, indication of temperature and pressure. So that's Easy ID and how you use that. I'm just going to move back over here to the webinar. Again, this was kind of a quick, just little reminder in terms of uranium deposits in general, but how we use the field spectrometer and what the data actually does for you. So using this, can really benefit you for your alteration mapping. You can really track those temperature changes of the white micas and even the clays. So I could have done the same thing with my kaolinite, my dickite, things like that, using the wavelength shifts and scalars. So this technology, it's non-destructive, it's quick measurements. And again, most of you here are using other data sets from other types of technologies. So this data is just going to work very well with that. So if you have any questions, you can email me directly. My email's here, lori.shelton@spectralevolution.com. If you have any specific application questions, how the technology can apply to your specific deposit, shoot me an email. If you have any questions on the technology itself, if you're wanting to know anything about the products, you can also email info@spectralevolution.com. And also make sure you follow us on YouTube and LinkedIn. A lot of times we post the webinars on YouTube. So if you want to go back and look at, previous ones, you can. So again, email me questions, let me know. If you have any requests for any future webinars, or if you, want to have a video call or anything like that, just let me know. So thanks everybody for coming, and we will talk later.